Hello, welcome back to the afternoon session for dynamical systems and ergodic theory. We have Michael Hochman, is an Israeli mathematician, currently a professor at Hebrew University of Jerusalem. He's known for his contributions to dynamical systems and ergodic theory. Hochman earned his PhD from Hebrew University of Jerusalem. He was an invited speaker at the International Congress of Mathematicians in 2018. 2015, he received the Erdős Prize from the Israeli Mathematical Union. 2018, he was awarded the Misha Brin Prize in Dynamical Systems. And now he's also winner of the Frontier of Science Award 2024. Please welcome.
Okay. So thanks for the introduction and thanks for the invitation. It's my first time on mainland China and it's been very impressive, very interesting conference. So I hope this is also interesting to you. We're going to talk about a paper that's by now 10 years old, where some ideas from additive combinatorics were applied to problems in fractal geometry. I don't like the term fractal geometry so much because it makes me think of sort of popular science. But I'll try to explain that fractal geometry, maybe you could call it by a different name, but it's a serious thing. It's a serious thing. I'm mainly going to try to explain what the problem is that this paper addressed and a little bit about how additive combinatorics enters the picture. And I hope I'll have time to explain what's happened since then, because since the paper came out, there's been a lot of activity around this type of problem, also a lot of further progress. So let me motivate this sort of by putting it in context. So let's talk about random walks. So random walks on RD. You start from some point x0, and then you generate the next point by selecting a random xi n plus 1 and applying it to xn. So xi n plus 1 is a random function, and you choose them independently and identically with the same distribution from some finite set of functions, f1 up to fk. And in this talk, the functions are going to be similarities. So f1 up to fk are a finite set, and each of the maps, all it does is it rotates, it scales, and it translates. It acts on RD. So you're choosing a map randomly at each time, and the distribution is some vector p of probabilities p1 up to pk, and we'll assume that the probabilities are positive, because otherwise you just remove the map from the list and it doesn't make any difference. So you're doing this random walk on RD, and there are three types of behavior, basically, that you can see. So the first case is when the maps are isometries. It's a special case of similarities. For example, maybe it's just a translation. So if the FIs are translations, then at each time step, you're just adding a random number to the previous number, and you're getting a random sum, an IID sum, and then you have the central limit theorem. And actually, the same thing happens also when these aren't just translations. You can allow rotations, and you can allow scalings. As long as you avoid certain degenerate situations, when you take the distribution of the random walk at time n, and you center it, and you scale it by root n, maybe with some constant, you converge to a Gaussian. Okay? A Gaussian on RD. And you also have a local limit theorem, so if you look at bounded sets and you look at the distribution inside of them at time n, then it converges to uniform. The second regime is when the maps contract. When the maps contract, you don't have to rescale. You actually have convergence of the distribution at time n of the random walk to some measure. It actually converges, but you don't have universality. So the measure, the limiting measure that you get depends on the characteristics of the maps that you started with. It doesn't depend on the initial point. It doesn't depend on x0, but it certainly does depend on the p's and on the maps. And then the last regime is when the maps expand. When the maps expand, typically the random walk will escape to infinity, and you can still study this. It's interesting to study this. You often have some kind of boundary theory if you look at it the right way. So for example, if you look at the direction of the vector xn from the origin, so you're really doing a random walk on the projective space, then you're basically studying random matrix products and their action on projective space, and the convergence of the random walk, of the distribution of the random walk to a stationary measure is a classical thing studied by Furstenberg and others. And it's a very interesting story. And actually, these aren't the only cases. Of course, the maps could be mixed. Some contract, some expand. If the average contraction is, if on average they contract, you'll be basically in the case of contraction. If they expand on average, you'll basically be in the expanding case. So this is more or less what you have. So we're going to focus on the contracting case. So you have k contracting similarities of RD, and you iterate them randomly, and you get some limiting distribution, which we'll call mu. And a mu of this type is called a self-similar measure. That's the fractal geometry name for this stationary measure. It's a stationary measure for a random walk. And you can characterize it. It's the only Borel probability measure that satisfies that mu is the average of, okay, for each of the maps, you push the measure forward by that map. So this is the notation for the push forward measure. And then you average it with the weights. And mu should equal this average sum. You can also write this as a convolution. If you think of P as a measure on the space of similarities, then this is just the convolution operation of the similarities acting on RD. And this is just the usual equation for a stationary measure. And okay, and you can also associate a set to this system, an attracting set. So the set X is just the support of mu. It's called a self-similar set. And it is the unique non-empty compact set that satisfies that X is the union of its images under the FIs. So this is just the set version of this. Okay, so just so we have something more concrete to think about, here's another way of generating a self-similar set or measure. You have some number of contractions on RD, and you take a really big ball. So imagine that this square is a ball. It doesn't, in this case, a square will do, but in general, you should probably take a ball. And then if you take the ball big enough, then because of contraction, it will be mapped into itself. And then when you map the big ball into itself with each of the maps, you get several copies embedded inside the original ball. So now if you take these three balls or squares, and you apply each of the maps of them to them again, then these three squares, when you apply the first map, they'll be mapped into the first square. You apply the second map to these three squares, they'll be mapped into the second square, and so on. So you'll get 9 smaller squares. And if you iterate this, you'll get a decreasing family of sets. Each set is the union of smaller and smaller squares, some exponential number of small squares. When you intersect all of these things, you get some kind of fractal set, and that's the self-similar set, which is the attractor of the system. And if you wanted to construct the measure, you could do the same thing. You would declare that the square has mass 1. Then you would split the mass, you would split the mass between the pieces according to your probabilities, P1, P2, P3. And then you would split the mass in each square proportionally. So if this was P1, you'll have P1, 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 P2, P1, P3, and so on. At each generation, it still sums to 1. And in the limit, you'll get a probability measure supported on this set, and that's the self-similar measure that we talked about before. Okay, so it's a classical problem to compute the dimension of these sets and measures. So what's the dimension of a set? I assume that everybody knows what the dimension of a set is, but I'll say it anyway. This is not the right definition of dimension. This is a definition of box dimension, which is not Hausdorff dimension, but for this type of set, it's the same thing. So if you've never seen what dimension is before, what you should think about is that the dimension is going to be alpha if the number of balls of radius r that you need to cover the set scales like r to the minus alpha plus some error in the exponent. So that is the definition. For these sets, that is a correct definition of dimension. For general sets, this is not the correct definition, but it is for these sets. And the dimension of a measure mu will be alpha if, for almost every point x with respect to the measure, the mass of a ball of radius r is r to the alpha plus an error in the exponent, a little o of 1 error. So, in RD, the mass of a ball scales like r to the d. D is the dimension. And for a measure, if the mass scales like r to the alpha, then the dimension is alpha. No, it's actually true in any case for these sets. This type of set, in the conformal case, for these sets, it's the same. It's not the same in general. Okay, and then another question that you can ask, so dimension is one way to measure how big a set is. You can also ask if the dimension is D, is maximal, then you can ask, does the set have interior, for example? You can ask, is the measure absolutely continuous with respect to the Lebesgue measure? If it is, then what's the regularity of the Radon-Nikodym derivative? All of these questions make sense and have been studied. So it just, generally I could say how smooth is the measure mu? And it's usually a hard question to determine. So the main conjecture in this world, in this type of problem, is that the random walk should spread out as much as possible, meaning that x and mu should have the maximal dimension and be maximally smooth as they can be. And we'll see that there is some limitation to how smooth they can be and how big they can be. But given those sort of trivial constraints, it's believed that they should become as smooth as possible. Unless there's some sort of specific reason, some specific algebraic obstruction. And this is similar to other conjectures or theorems in the area, right? In Ratner's theory, you equidistribute, the Horst-cycle flow equidistributes unless it's trapped inside of a coset or image of a coset or something like this. So it's the same type of statement. So let me tell you what is the, when I said it becomes maximally big, let me tell you what maximally big means here. What's the expected size of these things? So this is an old result by Hutchison. Let's write R sub I for the amount of contraction of the ith map. And then there's something called the similarity dimension, which is just the solution to this equation. You sum the Ri's to the power s, and you choose s so that you get 1. And Hutchinson showed that the dimension of a self-similar set is always bounded by this number, bounded from above. And that if the union is disjoint, so remember that X, the attractor, is characterized by the fact that it's equal to the union of its images. So if this union is disjoint, that's what's called strong separation, then the dimension of X is equal to S. And in this case, by the way, the set will be a Cantor set. Actually a Cantor set, it'll be totally disconnected. And there's an analogous statement for measures. There's an upper bound for the dimension of the stationary measure in terms of its entropy divided by its Lyapunov exponent. I'm not sure who this is due to. This isn't Hutchinson's result. I don't know who first stated this kind of thing, maybe Bowen, or maybe it's earlier. Anyway, it's a classical thing. So the entropy is just minus the sum of the pi's log pi, and the Lyapunov exponent is it's the sum. This is a typo. This should be sum of the pi's log r. So it's the average of the log of the contraction with a negative sign. And again, also for measures, if you have strong separation, if this union is disjoint, then you actually have equality and the dimension is equal to this formula. So in this case, it's very easy to compute the dimension. And let me explain sort of where this number comes from, where this S comes from. So let's go back to that picture we had before. Assume that we have 3 maps and they contract by 1/4. So then this number S, right, it's the solution to this equation. 3 terms, you sum 3 terms equal to 1/4 to the S, you want that to be equal to 1, so you get log 3 over log 4. That's just an easy computation. Now let's see how that comes out of the construction. So here's a cube, let's say it has side length 1. So at the second generation, you'll have 3 sets of side length 1/4. At the second generation 3 squared sets of side length 1 over 4 squared, and so on. So after n steps, you have 3 to the n cubes of side length 1 over 4 to the n. And we said you want to figure out how many sets of, this is basically the diameter of the sets. How many sets of this diameter do you need to cover the set? So you need at most 3 to the n of them, because that's, in the construction you had these small squares. They're basically balls. And they already cover the set. So the answer is that if you ask what power of the radius is 3 to the n, the answer is log 3 over log 4. And then you need a lower bound, so that just gives you an upper bound on the dimension, but it's not too hard to see that you can also get a lower bound. In this case, you can do it. It's not so easy actually to do it by hand, but you can also do it by hand. Okay, so a little bit more about the upper bounds. So Hutchinson's theorem tells us that the dimension is always bounded above by S. And because X is a subset of Rd, you also have an upper bound of D, because the dimension of a subset of Rd is never bigger than D. Same is true for measures. It's never bigger than D. So you always have this bound that the dimension of X is bounded by the minimum of S and D. And this is what we're going to call the trivial upper bound. And it's worth noting that this upper bound really doesn't look at all the information from the maps that generated the set. Okay, this bound only looks at the contraction ratios. It doesn't look, I mean, these are similarities, right? So it doesn't look at what the rotation was, if there was a rotation. It doesn't look at what the translation was. It just looks at how much they contracted. So it's really a sort of stupid bound. Okay, and I don't know if it's surprising or not, but it's not obvious that this is really going to be the dimension. And, okay, but it's an easy bound to get. And then, if this bound is incorrect, if actually the dimension is smaller than this number, we're going to say that there's dimension drop. The dimension is smaller than it's supposed to be. Okay, so why would the dimension be smaller than it's supposed to be? Well, what can happen is instead of the picture we had before, we could have a picture that looks like this. You sort of have some overlapping of the pieces. I'm lying a little bit here. I won't even tell you why I'm lying, but that's the disclaimer. I'm lying a little bit. This picture is not really accurate, but okay, so you iterate the picture, and then you get more overlaps, right? You get several overlapping pieces. Over here you have 3 pieces already overlapped. And as you continue, what could happen is that at some places, you're going to get maybe exponentially many pieces overlapping. If you have exponentially many pieces overlapping, then with one small ball, you can cover exponentially many of these squares. And then when you count how many balls you need to cover the set, you get a much smaller number than what you did when you just looked at, I mean, when you compute the similarity dimension, you're just pretending that each of these squares is really separate, and you cover it with itself. So you could get a much smaller number. And that's really what happens. It can happen that you get a smaller number. And here's an extreme case, okay? An extreme case of what I just described happens, okay, the following way. So if you have a sequence of n indices, okay, so 1 up to k is the set of indices of our maps. So if I have a sequence I of length n, then f sub I is going to be the composition of those n maps. And I'm going to say that exact overlaps occur if you can find 2 sequences of length n that are different from each other, but the compositions of the maps are the same. Which is another way of saying that the maps f1 up to fk don't freely generate the semigroup that they generate. The maps, if you compose them, you take all the compositions, that's a sub-semigroup of the group of similarities. It's not a group because we're not taking inverses, but it's a semigroup. And this is a generating set, but it might not be a free generating set. Okay, so exact overlaps just means that it's not a free generating set. You have relations inside this semigroup. And then it's a simple observation, like the one we had before, that if you have sufficiently many exact overlaps, if you have sufficiently many relations inside of this semigroup, then you are definitely going to get dimension that's too small. You're going to get dimension drop. Okay, and then the conjecture that sort of motivates this story is that in dimension 1 at least, exact overlaps are maybe the only reason that you would get dimension drop. Well, if you're okay, the thing if you're above the critical dimension, then you won't see the drop yet. But I mean, but if you're right, so really you should be interested in the case that S is less than D, and then one overlap already brings down the dimension. That's right. Yeah. So this question goes back in some form to Erdős in the Bernoulli convolutions problem, and then to some questions that Furstenberg asked, and it was stated explicitly in a paper of Karoli Simon in the 90s, I think. And up until about a decade or a decade and a half ago, most of the support that came that existed for this was to analyze parametric families of maps. And very often, what turned out is that typically you don't have dimension drop. If you have a parametric family of maps, and therefore you have a parametric family of sets and a parametric family of measures, for most choices of parameters, you get the correct dimension and you don't see any funny business going on. Okay, so to state the result, main result of this talk, I want to quantify, I want some sort of quantitative version of overlapping or not overlapping. So you fix a left invariant Riemannian metric on the group of similarities. Actually, it doesn't really matter what metric you take. Any metric that you can think of will be equivalent for the purpose of this definition. And we'll define delta n to be the smallest distance that you see when you compare two compositions of the maps of length n with distinct sequences of maps. So it's easy to see that this is a decreasing sequence, delta n, simply because the maps are contracting. It's also clear that you have exact overlaps if and only if the distance is 0 for some n, and once it hits 0, since it's decreasing, it stays 0. And for many choices of the metric, this will actually always go to 0 exponentially. But it could go faster. It might go faster, it might not. It depends on the maps. So this is some sort of quantitative measure of how fast, of how free the semigroup is. I mean, if this goes to 0 very quickly, then maybe the semigroup generated by these maps doesn't have relations, but it has sort of almost relations, because it has words that come very close to each other, much closer than you would expect. And we'll say that the system of maps, f1 up to fk, is exponentially separated if there exists some positive number rho so that delta n is bounded below by rho to the n. And again, this property doesn't depend very much on what metric you chose. It really is mostly irrelevant. This is not such a good name because exponentially separated makes it sound like they're very separated. But actually, you should think that rho is a very small number. So you just need a very weak exponential lower bound. Your rho can be as small as you want. So it's a fairly weak condition. And then the theorem is that in dimension 1, at least one of the following holds. And actually, we know from work that came later that they can both hold at the same time. But at least one of them holds. Either the dimension is the minimum of 1 and s, so there's no dimension drop, or delta n goes to 0 super exponentially. So if the conjecture was that dimension drop implies exact overlaps, this is sort of a quantitative version of that. I mean, it doesn't prove the conjecture, but it says that if you have dimension drop, then you may not have relations, but you have almost relations in the semigroup, in the sense that there are words that come very, very close together. And there's an analogous statement for measures. In fact, it's proved for measures, and then it's transferred to sets using a variational principle. Okay, so there's a corollary of this, which maybe I'll skip for lack of time, but it's not hard to, I'll just say it. It's not hard to see that if you take similarities that have algebraic coefficients, then dimension drop actually implies exact overlaps. And the reason for that is that you can choose the metric in a way that the distance between two compositions of the maps of length n is a polynomial of degree n in their coefficients. And then it's a classical thing from, I don't know, number theory or the Fantin approximation, that if you have a polynomial of degree n in a fixed set of algebraic numbers, then either it's 0 or it's positive with a lower exponential bound between it and 0. So that's basically proof. Okay, so that's the theorem, and now I'd like to shift over and try to explain a little bit about how additive combinatorics enters this picture. Okay, so let's go back to our overlapping self-similar set or measure. Right? You iterate the construction for some time, and then you look at a small piece. Look at a small piece of it. Suppose that there's a dimension drop. So the dimension is smaller than what it's supposed to be. Then what that means is that there are going to be many balls, many small balls, where you see exponentially many of these little copies of the whole thing. By the way, you might wonder why I'm showing you a two-dimensional picture when the theorem is about dimension 1. And the reason is it's very hard to draw these pictures in dimension 1. So that's the only reason. Okay. So there'll be lots of balls that contain exponentially many small copies. And you can show that somehow the fact that this thing is invariant under some dynamical process says that this small piece should in some sense resemble the whole thing. I mean, certainly it's true that the dimension of this small piece is equal to the dimension of the whole thing, but also at finite scales. Like if you look at a much finer resolution at this little piece, it'll look the same as the whole thing did at a comparable resolution. But on the other hand, locally, what do we see inside this ball? We see exponentially many copies of the whole thing. More precisely, the union that you see here can be written as lambda times x. Right, what is lambda times x? You just take a union. Lambda is the maps that are responsible for these copies. So it's a finite but exponentially large family of maps. And lambda x is just you apply every map in lambda to the set x. Or in other words, you look at all the points gx, where g is a map in lambda and x is a point in the set x. Right, and so this brings us to the philosophy, which maybe you've heard in other talks in this, I've heard it in at least one other talk in this conference, that when you take the sums of sets or the products of sets, it's a smoothing operation. When you sum things together, when you convolve measures, they become smoother, okay? And so what we'd like to say is, well, this piece contains exponential, it's a product of two sets, the original set x, and an exponentially large set of maps. And therefore, what we see inside of here should actually be smoother or bigger or have a higher covering number than the whole thing. And that would be a contradiction, because we said this little piece should resemble the whole thing. Okay? So, okay, so now let's switch gears and let me tell you a little bit about additive combinatorics in general. Actually, the way I wrote this in the higher dimensional case, you have a family of maps. But if you think about it, if we were doing this on the line, and if, let's for simplicity suppose that all the maps contract by the same amount, all these little copies would differ from each other just by translations. Okay? So this would really be a sum set and not a product set. And so let's talk about sum sets. One of the problems in additive combinatorics that you may have heard about, and if you haven't, you should look it up, is the problem of understanding what is the structure of sets A and B, so that the sum set is not much larger than A. Okay, so the sum A plus B is the sum of all pairs, x and A and y and B. And suppose that this isn't much larger than A, these are finite sets, what can we say about the structure of the sets? Okay, so you have to say what I mean by not much larger. Okay, so one possibility is what appears in the Freiman-Reuser theorem. They describe the structure, well, actually it's not exactly the Freiman-Reuser theorem, but the question is, what can you say about the structure when A plus B is at most a constant the size of A? Maybe you only doubled the size. Maybe it only times 1,000. And the answer is that in this case, the sets A and B are close to basically a linear image of a product set in a higher dimensional Euclidean space, a product set in a lattice. So it's basically some kind of, there's an arithmetic structure. After you take the projection, you also have to throw out some points. So these are going to be subsets of the projection, large relatively large subsets of a projection of a box in a lattice in a higher dimensional Euclidean space. And there's been a lot of progress on this problem going back to Bourgain and Green and Tao and others, and actually very recently there's been further progress in really getting the sharp constants here. But this situation isn't what we need, because we're looking at exponential scales or logarithmic scales. So what it means for us to not grow very much is the case when a plus b is bounded by a to a small to 1 plus a small number. So not just a constant times a, but a power of 1 plus epsilon. And then this brings us to there's been work on this too. Bourgain, starting I guess in the late 1990s or the early 2000s, was working on a whole technology for analyzing sets of this type. He had a certain multi-scale analysis that he brought to bear on this problem as part of his sum product results. Now, let me just say that you could, in principle, analyze this case using this case. You just say, okay, C is going to be a power of the size of A. But if you do that, then what you get isn't useful. You need to do something else. And so in this case, you don't get algebraic structure. You get a different structure. And the theorem that goes into the additive combinatorics result that goes into the theorem about dimension of self-similar sets is a version of, it's a variant of Bourgain's result. And instead of looking at the size of sets, we're going to work with measures. And the way that we measure the size of a measure is using entropy. So let me briefly, I hope everybody knows what entropy is. If you don't know what entropy is, just think of it as the log of the size of the support of the measure. Okay, these are finitely supported measures. Take the log of the size of the support. Okay, I hope some of you know what entropy is. So if you have a Borel probability measure on R, and K and L are two integers, K bigger than L, then the entropy of mu at scale 2 to the minus K is just the Shannon entropy of mu with respect to a partition into intervals of diameter 2 to the minus K, or of length 2 to the minus K. And the conditional entropy, mu at scale 2 to the minus K, conditioned on 2 to the minus L, is the difference of the entropies. If you've seen this before, then there are other definitions that you know. And if you haven't seen this, the way to think about this is if you normalize this quantity by 1 over K minus L, then it's some kind of substitute for dimension, because it's always going to be between 0 and 1 up to some error that goes to 0 when K minus L goes to infinity. And actually, when this number, this normalized number is close to 1, what it means is that when you condition mu on a typical interval of length 2 to the minus L, what you see is almost uniform at this scale. And when this quantity is close to 0, what it means is that conditioning mu on a typical interval of size 2 to the minus L is, well, it's not quite true that it's concentrated on an interval of length 2 to the minus K, but maybe I should say it's concentrated on a sub-exponential number of such intervals. So it means that it's quite concentrated. Okay, so this is the theorem about convolution. It looks slightly technical. I'll try to explain it. So you fix two parameters, K and epsilon. So for any K and epsilon, you can find a delta. So the following is true whenever n is large enough. Suppose that you have two probability measures on the unit interval. And suppose that when you convolve the measures and look at the entropy at scale 2 to the minus n, and you normalize it by 1 over n, you get the same entropy as you would have had before you convolve plus delta. So remember that entropy is sort of like the log of the size of the support. So before we were talking about this type of condition, say a plus b is bounded in size by a to the 1 plus epsilon, or 1 plus delta. If you take logs, then you get something that looks like this. Okay? It's just we've taken logs, so you get the delta coming out as an additive term instead of in the exponent. So assuming that mu and u satisfy this, then when you look at the scales from 1 to n, you can identify two sets of scales, two types of scales. E1 and E2 will be sets of scales. And together they'll cover almost all of the scales. So they'll cover 1 minus epsilon of the scales. And they have the property that for every scale I in the first set, when you look at the conditional entropy of mu, conditioned on intervals of size 2 to the minus I, so that's this I, at a scale that's k times smaller, then you find that entropy is almost maximal. It's bigger than 1 minus epsilon. So it means that at these scales, mu looks almost uniform. And at the other scales, the entropy of mu, the other measure, at scale I, conditioned on scale I and with the entropy taken at scale I plus k, the entropy will be small. So it will be almost concentrated. It will be very concentrated. So what does this mean? Okay, here's what this really means. You convolve two measures, nu and mu. And the entropy didn't go up at scale n. So you can learn that there are two types of scales. At some of the scales, the measure nu is going to look very concentrated. So what is this picture? I'm thinking of a measure on the unit interval as a weighted binary tree. Binary, or you choose your base. So you split the mass of a measure, it gives some mass p to the left half and 1 minus p to the right half. So that gives you weight p and 1 minus p on the first level of the tree. And then the measure on the left half is divided in some other proportion, p and p prime and 1 minus p prime. So you get weights on the rest of the tree and so on. So you build a binary tree. And if you go down to scale 2 to the minus n, then you get a binary tree of size, with n levels. So that's what these pictures mean. And what the theorem says is that when the entropy didn't go up, the reason is that at some scales, when you look at what happens, you take a node at this level, say, and you look what happens k levels down, you see something that's quite concentrated. And when you take a node at this level and you look k levels down, you see something that's quite concentrated. I mean, this is a picture sort of the, I've made the edges with low weights disappear in the picture. That's sort of what this is saying. On nu, this is the measure nu. So we had, right? So nu convolved with mu was less than the entropy of mu. No, it's not given mu. So we're saying that at some scales, mu looks very concentrated. No. Well, given that this equation is true, given that you have yeah, I mean, this is an assumption about both the measures and the relation between them. Okay, so again, at some scales, mu looks concentrated. At the complementary scales, mu looks as though it's almost a uniform measure. And that's the structure that you get when you know that the entropy doesn't go up. And then sort of the punchline is that self-similar measures can't look like this. They never look like this. Because self-similar measures look the same everywhere, at every scale. So if you had a self-similar measure that at a positive density of scales looked as if it was uniform, it would really be uniform everywhere, and its dimension would be 1. So if you have dimension drop, then there are almost no scales in the set E1. There are almost no scales at which this happens. But that means that almost all the scales have to look like this, and that means that mu has almost no entropy, because at almost all scales, it looks highly concentrated. So I think it's probably difficult in such a quick talk. If you take Lebesgue measure convolved with itself, well, then here there'll be almost no scales. And here you'll have almost all the scales. So you'll simply get no information about mu. If you take any measure convolved with the Lebesgue measure, you'll get a full dimensional measure. So then that means that I'm not making any claim that both of these sets of scales are large. Only their union is large. Also, if nu is just one atom, then you get no information about mu because all the information is in the set E2 of scales at which nu is concentrated. Okay, I know this is a lot to take in a quick talk, but I tried. I'd like to, in the last 5 minutes, tell you a little bit about what happened after this result, okay, about what's happened since then. So one application is to Bernoulli convolutions, and maybe this is where the most dramatic progress has been. So what are Bernoulli convolutions? You take a parameter lambda between 0 and 1, and you write nu lambda for the distribution of this random real number. So you take the sum from 0 to infinity of lambda to the k, but with signs that are chosen randomly, plus or minus 1, with probability 1/2. And if you look at this number, then you can take out the first term. So the first term is plus minus 1. And then you notice that this sum, this random variable, is equal to this random variable plus this one, right? This random variable takes values 1 or minus 1 with probability 1/2. This random variable is just the original one scaled by lambda because you have independence between this variable and these. So the distribution of this is by definition nu lambda is equal to conditioning on the first digit is equal to, with probability 1/2, the average, well, the distribution is with probability 1 is the average with weights 1/2, 1/2 of itself scaled by lambda and translated by plus minus 1. So it's a self-similar measure. That's exactly what a self-similar measure is. And the trivial upper bound, the similarity dimension in this case, is log 2 over log 1 over lambda. And when lambda is between 1/2 and 1, the right-hand side is going to be 1. So potentially, when lambda is between 1/2 and 1, you could have a measure which is smooth. Actually, you can, in that case, you can show that the support of the measure is the entire unit interval. And it's a classical problem. It goes back to Erdős in the 1930s, is to figure out which lambdas give you an absolutely continuous measure, nu lambda, and for which lambdas the dimension is 1. Okay, so I'm going to skip the history. It started a little bit before Erdős. Okay. So the theorem that I showed you before implies that if you ask for which parameters lambda is the dimension of nu lambda less than 1, you can derive from the theorem that I stated that the dimension is 0. The dimension of the exceptional parameters is 0. But in fact, since this paper came out, there's been really tremendous progress on this. So Guial and Value in 2019 derived a more quantitative version sort of this technology. And they showed that when the dimension of nu lambda is less than 1, there's actually an algebraic number, lambda prime, which is extremely close to lambda, and which also has dimension drop. And maybe what I should say is that the conjecture about these measures is that the only case where you have non-smoothness or dimension drop is when lambda inverse is a Pizot number, is a certain kind of algebraic number. Yeah, so that theorem tells you that when you look at an algebraic lambda, then you know that okay, so one reason is that you're above the critical value. But you can have exact overlaps. For algebraic lambdas, the conjecture is correct. Okay? For algebraic lambdas, the dimension will be 1. So that the dimension is less than 1. Okay, so that means that this lambda prime, for this lambda prime, there are many exact overlaps. Absolutely. Absolutely. Sorry, yes, there should be a prime on this lambda. Thank you. Sorry, yeah. There must be, yes. There must be, yes. Okay, so actually for dimension, this problem is now completely solved. So Peter Value in 2019 proved that the only lambdas between 1/2 and 1 for which the dimension of mu lambda is less than 1 are algebraic numbers. He doesn't get a characterization of exactly which algebraic numbers these are. You can say that they're roots of polynomials with coefficients plus minus 1, but that doesn't yet say that they're Puiseux numbers, so that's still open. But this pretty much resolves the question for Bernoulli convolutions and the dimension question. For smoothness, so shortly after my paper came out, Pablo Schmerkin used it together with the Fourier analytic argument to show that the set of parameters lambda for which mu lambda is singular with respect to Lebesgue is 0. So previously there had been some bounds that show that this dimension is less than 1, at least in certain subintervals of 1/2, 1, but this really gets us down to dimension 0. Again, the conjecture is that there's countably many exceptions. So dimension 0 is still more than there should be. And then after this, in a slightly different direction, Peter Value found various conditions on algebraic numbers that will ensure that mu lambda is absolutely continuous. Some conditions on the Mahler measure of the numbers I won't go into. And then, okay, what happens in higher dimensions? So I prepared some slides, but I won't show them to you. The conjecture is not quite right in higher dimensions. You have to rule out some other phenomena that can happen. One thing that can happen, I can show you a picture. Suppose you have a system of contractions like this in the plane. You have many, many maps, but all the images of the big square sort of accumulate on these two columns. If you iterate it, what you'll get in the limit is sort of a product set. If you have many, many maps, and they all contract by the same amount, then the similarity dimension will be much bigger than 2. And so dimension drop just means that the dimension is less than 2. But this example clearly has dimension less than 2, because when you project it to the x-axis, you get a tiny Cantor set. So what you need to do to get around this issue, if we let ui denote the rotation part of the similarities, then you have to say not that either there's that dimension drop implies exact overlaps. You have to allow one more possibility. Either the dimension is full, there's no dimension drop, or there's exact overlaps, or there could be a ui invariant subspace on which the intersection with the set has full dimension. And that's what happens here. In this example, we have this vertical direction. It's an invariant subspace for the rotations, and when you intersect it with the set, you get a set of full dimension. So that's sort of the conjecture, and there's a preprint. It's been a preprint for a long time. It'll appear eventually of mine where the analogous, it's not the conjecture yet, but we replace exact overlaps with super exponential convergence to 0 of delta n, and that statement is true. Okay, maybe I think I'm out of time. Am I out of time?
We started answering our questions about higher dimensions.
Okay, so maybe I'll tell you 3 more results that happened after the paper. So as I told you in the beginning, there's another regime that's interesting, which is when you take an expanding random walk and you look at the boundary behavior. So the simplest case of this is when you do a random walk, a matrix random walk on R2, and you look at the projective space. So it's the one-dimensional projective space. You're just applying matrices and looking at the direction of the point. And then what you converge to is called the Furstenberg measure on the circle. And in 2017 with Boris Solomiak, we proved analogous results for this measure. So if you take a strongly irreducible SL2Z random walk on the projective line, then if you assume exponential separation, you'll get that there's no dimension drop. You get the correct dimension. Another very beautiful result was proved in 2019 by Pablo Schmerkin using the same philosophy, but a different version of it, a more quantitative version. He proved what's called the Furstenberg slice theorem, which is a theorem about intersections of certain fractal sets. And I won't go into details, but that question had been open for 50 years and has been resolved. At the same time, Meng Wu found another ergodic theoretic proof of the same result. So there are actually 3 proofs of it now. And then in another direction, you can ask what happens if you leave the conformal world. You don't look at similarities, but you look at affine maps instead. When you have affine maps, the thing that becomes much more complicated is that, okay, you start doing your construction, you take a big ball, and then your affine maps map it into itself, but now they distort, right? So now you're going to get ellipses. And at the next generation, these ellipses are going to get more and more eccentric. So this brings us into the world of smooth ergodic theory, where you have different Lyapunov exponents in different directions, and things get much more complicated. So in this case, even computing the dimension under strong separation was open forever. So we solved that in dimension 2 with Balázs Bárányi and my student Ariel Rapoport in 2019. And then later with Ariel, we also proved the exponentially separated case. In R3, we can do the strongly separated case. We can't do it in higher dimensions yet. There's a problem there. So that question is still open. It's still beyond what we can do. There have been many other results I won't tell you about. I'll just tell you that the main conjecture is still open. We don't know that exact overlaps is the only reason for dimension drop. Thank you very much. Sorry? Nonlinear maps. We don't know how to do nonlinear maps. The only case of nonlinear maps that we know how to do is the result I mentioned with Boris Solomiak, where I said we do a matrix random walk on R2 and look at the directions, at the projective space. But if you think of this as maps of the line, then they're really just fractional linear transformations, and then they're not linear. But the key thing is that we need, so you see when you compose the maps, we want all the compositions to live in a finite dimensional group, in a Lie group. And there aren't that many examples of, when you take nonlinear maps, somehow when you compose them, you're not confined to any finite dimensional manifold of maps. And the way that we know how to deal with these questions in higher dimensions, somehow this theorem about convolution, in higher dimensions, what you have, nu is going to be a measure on, the affine group, let's say, of Rd, or some other group, and mu is going to be a measure on Rd. And then you have to analyze these convolutions. If you take nonlinear maps, not just general smooth maps, then this is going to be a measure, on C infinity, let's say, or it's going to be an infinite dimensional space. And then somehow we don't know what to do. We lose control. So that's a good question. I think nobody's managed to do anything.
Probably conformal IFS are easier than nonlinear, because I'm wondering if you know any results.
In the complex plane?
No, just Rn.
Oh.
Self-control, conformal iterative function systems.
Well, there aren't that many conformal maps in Rn. I think so, but even complex maps, right? Even just holomorphic contracting maps, that's as conformal as you could want, right? We don't know how to do it if the maps don't lie in a finite dimensional group. So the answer is we don't know how to do it.
Maybe 2 different questions, but on the same thread, what about unipotent maps? Why are those hard? I don't.
Unipotent maps.
No, I just mean like in R2 1101.
Well, you want them to contract. You want them to contract, but that
rotations don't contract. You allow those.
Well, we want. Are you talking about the sort of the escaping to infinity case, or the?
Perhaps I didn't understand, and maybe that's the problem here. But I thought you allowed dilations and rotations and affine transformations. I'm just saying, what about shears
Yeah.
also?
Yeah. Okay. So
Or maybe I
right.
misunderstood.
No. I understand what you're asking. So right, one of the generalizations I mentioned on the last slide is to affine maps, and affine maps allow that also. Of course, I still need them to be contracting because if they don't contract, they're not defined. So, but I could take something certainly like this. No.
Yeah.
That would be fine.
Okay.
That would be fine. Again, a group with only this maps of this structure would create complications because you have invariant linear subspaces, and then things become more complicated. So actually, I mean, a group only of these things would maybe we couldn't handle it. I don't know. But then if you throw in one more map, then it should work.
Okay. Can I ask a second question? Is that okay, or is there something else? So in the D equals 1 case, you used arithmetic combinatorics as a key tool. So what's the kind of, what do you, in the D bigger case, what do you do? Do you have like arithmetic combinatorics on Z to the D or something, or I don't know?
Yeah, no, so actually we cheat. Yeah, so okay, so first of all, there's a theorem in RD so if you take a convolution, you have two measures, mu and mu, which are probability measures, let's say, on the unit cube. And you assume that the entropy of nu convolved with mu at scale 2 to the minus n is bounded by the entropy of nu convolved of just mu at the same scale plus delta. And you normalize it the way you should. Then you get a similar structure theorem, except that, right, in this picture, we said that we have like some scales where mu is very concentrated, then we have other scales where mu is very uniform, and this is no longer the only thing you have to take into account. At each of the scales, there will be a subspace of some intermediate dimension, and the uniformity could be, so here you'll be concentrated on that subspace, and here you'll be uniform on that subspace. And the subspaces can change from scale to scale. So that's sort of the structure that you get from additive combinatorics. And then, yeah, and then when you're working, that's a linear statement. That's for convolution. So that's really a sum set statement, right? Then when you want to work with other maps, even with similarities on RD, like I said, you end up working with a measure on the group convolved with a measure on RD through the action of the group on RD. And then what we do is we cheat. We linearize the action at small scales and apply the linear result, apply the additive result. So we somehow avoid working actually in a nonlinear group by linearizing it at small scales. We go to a small scale, we look at a group, a Lie group acting on RD, or something, a similarity is acting on RD. When you look at it at a small scale, it looks like a linear action. I mean, it is a linear action, but it looks like you just differentiate and it becomes addition. So.
Okay, thank you.
Maybe I want to end with one question for students. The main conjecture is still open in one dimension, right?
Yes.
So if I could like build a Cantor set and they have these maps have overlaps, could the dimension drop without being exact?
Yeah, if somebody wants to solve that, that would be great.
Okay. All right, let's thank Mike Hochman for a beautiful talk. Thank you. Our next talk is at 45 in 16 minutes.